Welcome to this video by Exact Education. The purpose of this video is to explain what calculus is and how we use calculus to solve problems in engineering. Arithmetic is about basic computation, manipulating numbers, addition, multiplication. If we scaffold up, algebra is about finding patterns between numbers. For example, the Pythagoras triangle, to find the length of a longest side by taking the square and the sum of the other two sides. Calculus is about finding patterns within systems, within formulas. Algebra and calculus are effectively a problem-solving duo. Calculus finds formulas, algebra solves them. Calculus is expanding our understanding of how processes in nature, engineering, science operate. Differential calculus is all about breaking a system, a function down into small, manageable pieces to find out how a system is changing at any point, at any instant. It's about finding the rate of change of a system at any instant. Integral calculus is joining small pieces together to calculate areas and volumes. So the trick is we break a system down into manageable chunks so that we can analyze it and solve problems. Isaac Newton and independently Leibniz developed calculus back in the 17th century. Newton in particular took science from the qualitative into the quantitative world. So for example, developing Newton's laws of motion, Newton's laws of gravity, whereby he was explaining the universe in terms of formulas and numbers. A true genius. For a linear system, we don't need to use calculus. In a linear system, its definition is the rate of change is constant. It's a straight line. However, if we have a nonlinear system where we've got curves, how do we find out the rate of change at any point on that curve? If we have a data set such as on the left-hand side here, we can see from that data set, if we take any coordinate pairs and we want to find out the slope, the gradient, the rate of change between any pairs of coordinates in that system, we can see that, for example, from x equals 0 to x equals 1, there's a step change in 1 and x, step change in the horizontal, how much change in the vertical, 8 minus 5, 3. So the gradient is 3, it does not change. Linear system described by the function mx plus c, where m is the gradient and c is where it crosses the y-axis. However, if we have a non-linear system, we've got a curve in this example here, how do we find out at any instant what the rate of change is accurately? We can do it graphically, but we want to know how to do it accurately. If we want to do it graphically, we can see between x equals 0 and x equals 0.2, we have, albeit the rate of change is constantly changing, but we can see that the rate of change is positive. We gradually reduce the rate of change till we get a peak here, and the rate of change is 0 at a peak. So the definition of a peak is at that instant, there is no vertical change. So we have a rate of change of 0. When we go from a positive rate of change to negative rate of change, there must be a positive peak. Between x equals 0.2 and 0.8, we have a negative rate of change, and it gradually slows down till we get a negative peak. So we can see quite a lot of information graphically, but we want to do it as accurately as possible. If we have a graph of displacement, vertical against time, horizontal, we have 2 points on that curve far apart, A and B. We can calculate the average velocity, the difference in displacement over the difference in time, and that would give us the average velocity between A and B. It gives us some information, but it's not a particularly accurate one in terms of it misses out how the velocity is changing in terms of it's got a peak here. So if we bring the points closer together between A and B now, again, it's an average along that straight line. In terms of a linear system, we get an average velocity between A and B. It's more accurate now. Why is it more accurate? Because points A and B have been brought closer together. So here's the trick. We bring the points A and B closer and closer together, and we gradually get to a point where A to B line is a straight, tiny straight line, infinitesimally small, and we get the rate of change at any point on that curve. If we use the analogy of an archway, we can see here that what our eye tends to see is a smooth arch, a smooth curve in here. If you look closer, it's made up of bricks. These bricks do not have curved lines on them. They've got straight edges on these bricks. You can see that this curve is made up of a series of straight lines. So the way we analyze rates of change on a curve is we break the curve down into a sequence of small straight lines and compute the rate of change for a tiny straight line by taking delta y divided by delta x. And this was a trick of differential calculus. So what we're doing is taking 2 points anywhere on that curve, A and B, bringing those points closer and closer together. So we're effectively zooming in. If we zoom in and in and in, we gradually get more and more to a tiny straight line, and we can compute the gradient of that tiny straight line by looking at the difference in the vertical divided by the difference in the horizontal step, and we can compute at an instant what the rate of change is. Integral calculus, on the other hand, is taking tiny pieces, adding them together to work out areas and volumes. Integration, differentiation, they are the inverse of each other. How do we find the area under this curve? Well, we can do it one way by dividing this area up into tiny, tiny manageable chunks. So you could divide it up to equal shapes of squares or equal shapes of rectangles and fill up that area with those equal shapes and just add them all up, and you will get a ballpark figure, which is numerical integration, which will be reasonably accurate but not exact. So for example, if we split our area up into rectangles of different height, the height is dictated by the position on the curve. They've got equal width. If we only have a few rectangular slices, add up the areas of rectangles, which is a simple computation, then we can get a sum which gives us the area, which is a ballpark figure, not particularly accurate. How do we get it more accurate? We make the slice width smaller and smaller at the downside of giving us more summation. If we make the step size, the slice width of the rectangle infinitesimally small, then we will get an accurate result. So the more slices, you get more accuracy at the price of having more additions. If you use Excel, the more additions is not particularly high price. It's very easy to quickly manipulate an Excel spreadsheet to give you the summation. So what the trick is, we make the slice width of the rectangle infinitesimally small, and we follow rules of integral calculus to get an exact answer. This is the symbol for integration. So here we're integrating a function of x with respect to the variable x. Integration, differentiation, they are the inverse of each other, and we follow rules to go between the two. Rules of integration are we add 1 to the power and divide through by the new power. If we don't have limits on the integral, So we're not integrating to find areas or volumes between specific limits. Then we need to add a constant. The definition of a constant is its rate of change is 0. So there may be a silent constant in here that we need to take account of when we're doing the integral. So for example, if our function is x cubed, if we want to find a general equation for the area under that curve, we add 1 to the power x to the 4 and divide through by the new power. Volumes. Again, this is areas in 3 dimensions. So we take the formula we're given in 2 dimensions and revolve it round either the x or the y axis to give us a particular volume. We've got 2 options again. Again, we add tiny, tiny small pieces together, fill up that volume to its full and then add up all the multiple copies of these pieces, and you would be able to get a ballpark figure. Very tedious. You can get it reasonably accurate if you use tiny small pieces, but not particularly practical, not particularly sane, but there's nothing to stop you doing that. The sane way to do it is to use rules of integral calculus. The easiest way is to use the disk method. So for example, if we have a function y equals x in 2 dimensions, that straight line here, if we revolve that straight line around the x-axis, we create a volume of a cone as shown here between x equals 0 and x equals b. How do we calculate the volume of that cone? So as we suggested earlier, for example, if you made up multiple copies, exact copies of a tiny cube volume that you know the volume of, fill it up with dozens or hundreds of these cubes to get full, tip them out and add them all up, you'll get a ballpark figure. Numerical integration. Gets ballpark figures, gives you an indication of the volume, but not particularly accurate. If we use rules of integral calculus, we can get an exact figure. So for example, in 2 dimensions, if we have a function shown by that red line there, which is non-linear, it's not a straight line. If we take that line between certain limits in x and we revolve it around the x-axis, we will create this volume shape here. The trick is to notice that if you look at the face of the solid of revolution, it's a circle. So what we can do is we can take slices through this volume, and for each slice we'll have the area of a circle. So the volume will be determined by the thickness of the slice. So if we take slice through to get multiple discs, all those discs are going to have a slightly different radius here, but we know that the radius of a circle is pi r squared, and if we added up all those discs together, we would get an accurate figure. So the trick is, again, to make the slice of the disc infinitesimally small. So for example, that's just repeating the previous slide. It's not really necessary to be in there. Why is the area of a circle pi r squared? Well, if we take rings of increasing radius, then we form the face of a disc or the face of a circle. If we assume that we know that the circumference of a circle is 2 pi r, if we unwrap all these rings that have been added together, then we can see that it forms a triangle here, and the length of each of those rings is 2 pi r. Then we can see from a basic computation, just getting that area, it comes out to be, if we do length times height and take half of it because it's a triangle, we get pi r squared. So again, what we're doing here is breaking an area of a circle down into numerous cumulative rings to show that it's pi r squared. We need pi r squared because what we're doing is slicing up this volume into discs. each disk will have a different radius determined by its function in 2 dimensions, for example, 1 over x. So the area of each of the disks will be pi r squared. So r is the y dimension that's given by a function of x. If we replace r by y, y by the function of x, in this particular example, we get an area is pi times 1 over x squared. If we use rules of integral calculus, and we want the volume between x equals 1 and x equals 2, then we integrate the function between those limits. And it's a function of x now, given by the 2-dimensional formula. If we use rules of integral calculus, we add 1 to the power and divide through by the new power. So we've got 1 over x squared, which results in our function x to the minus 2. If we add 1 to the power, we get a result of the integration. Minus 2 plus 1 gives us a power of minus 1 divided through by the new power. So this is the answer to the integral here, but we want to calculate it between these particular limits of x equals 2 and x equals 1. So we calculate x to the minus 1 for x equals 2, and then subtract it when x equals 1. And then if we go through that computation, it results in the answer of pi divided by 2. So we put the limit for 2, we subtract the equation for the limit of x equals 1, compute it down to pi over 2, and that is the exact answer. If we want to verify that numerically without filling up the volume with physical tiny pieces of cubes, we can use the digital tools such as Excel now to give us a confidence level and do numerical integration. What's being done in this spreadsheet here is what's being put into the spreadsheet is values of x. X is going from 1, 1.1, 1.2, so on, to x equals 2, and so on. What's important to understand is the step size of x, the width of the disk is 0.1, and what we're doing for each value of the formula, the area of a circle, we're calculating for each value of x, we're calculating the area of a circle. And what we do is then multiply by the step size to give you the volume of the disk. If we add up all these volumes, there'll be 10 of them. If we've got steps size of 0.1 between 1 and 2, we add up the volume of those 10 disks, it comes out to be 1.45. The exact answer is 1.57. It's fairly close. It's not that far off. It gives us a ballpark figure. If we want to find out how close it is, that numerical answer is only 7.2% out from the exact figure of volume. How do we reduce the inaccuracy, if you like, get that figure of 7.2% down? How do we do that? So how do we do that is we make the disks thinner and thinner at the price of having more summations in the Excel. Having more summations in the Excel is not a particular penalty. It's very simple just to extend an Excel spreadsheet out with different step sizes. So 0.1 steps, if we divide that by 2, then we've not just got 10 additions, we've now got 20 additions of disks, but we get it more accurate, 3.68%. If we divide it by 2 again, we've now got 40 additions, but we get it more accurate. If we divide it by 2 again, we've now got 80 additions of disks, very thin disks now compared with here, but we get it more and more accurate. Numerical integration is a good way of verifying your integral calculus answer to make sure that you haven't made a mistake going through the computations. Similarly, if we want a slightly different shape and we want to revolve a function around the y-axis, then we can do that in the same way, except we've just got to swap over the x and y variables. so that we get an integral in terms of the y direction instead of x. Thank you for watching, and I hope that's been beneficial to explain how we use calculus and rules of calculus.